All right, so now let's talk about the structure of covalent ceramics. So most of what we talked about so far has been based on ionic. And so move to covalent. And so I want to start talking about hybridization. So covalent ceramics often involve what we call orbital mixing. And that is what it kind of sounds like, right? We have two orbitals in a given material, such as the 2s and the 2p, and they merge together to form one common orbital with the same energy level. This is known as hybridization, where typically S and P orbitals that are somewhat close in energy can mix to form what we call a hybrid orbital. So that's what we have down here. So that's the gist of this hybridization. So this is going to be important for a number of covalent materials, and let's start with carbon. So carbon can actually form into sp3. So this is where we take one s and three p orbitals and hybridize them together. And so we have what is shown here. And if you count out the number of electrons, then carbon would fill, it would have 4 electrons there. So one in each of these orbitals. So you can see that they're half filled. So this type of structure, if we can visualize it in orbitals in space, it would look something like this. So each one of these lobes, each one of these orbitals represents one of these lobes or nodes, and basically has 1 electron apiece. And so this is kind of what it looks like in space, and you can see this angle of 109.5. And so you might be able to see where we're going with this, but this shape is important. So each one of these is half filled, and therefore it's going to want to bond and basically share electrons with each one of these nodes. And so the simplest arrangement for carbon would be to have something with 1 electron at each of those positions. So if we take a hydrogen here, so it has 1 electron, this has 1 electron, they can share those 2 electrons and get to the noble gas configuration and do that on every lobe. Then we have CH4, and we share electrons, so it's covalent bonding, and we reach the stable configuration because we're filling up these orbitals, these hybrid orbitals. However, for us, we're not necessarily worried about CH4 yet. We are worried though in looking at structures. And so for this sp3 configuration that we see, this happens in carbon. And if it bonds with itself, the arrangement that it forms is here. So again, each one of these is a carbon. And if we consider these kind of bond angles with the other carbons, you'll see that it matches with this configuration over here. So when carbon bonds in this way with itself, and each one of these lobes bonds to another lobe and a nearest carbon atom around it, it forms into this tetrahedral arrangement, right? Which is the same bond angle, the same shape as what we see over here. And this structure, based on this hybridization, has a coordination of 4, which we know from our previous charts. And it forms from this sp3, and it's known as the diamond cubic structure. So you might guess it, but this is basically what the structure of diamond looks like. You know, you've all heard that diamond is made out of carbon, same as graphite, but just in a different structure. And so this is that structure. And so if we look at this, since the coordination is only 4, the packing efficiency is rather low. So that's something to sort of keep your mind on. And then again, you can visualize it as FCC, right? You see everything is in the simple cubic array and also the face center. You see all those, but it also has 4 other atoms in the tetrahedral sites. So we can kind of view it as 1/2 tetrahedral filled in that same kind of sequence we did in the previous one. But again, even though you're kind of seeing that they're simple cubic and face-centered positions, that doesn't mean it's close packed like FCC. Having the interstitial and the tetrahedral sites expands the structure and opens it up and results in this low packing efficiency. All right. So the other type of hybridization that's common in carbon is what's known as sp2. So these are kind of the energy level diagrams. We don't need to go into them a bunch, but basically what happens here is that the ground state of carbon that you can see up here transforms into what you see down here, where you have one 2s merging with two of the 2p to get us sp2 orbitals at this level, and there would be three of them, and then one of the p orbitals is unperturbed. It's left the same. And the same thing, we have four orbitals total. Each one of them has one electron, so it's half filled, just like we saw in sp3. And so visually, the sp2 orbitals are going to look like this. So we have those lobes. Again, each one of these has one electron. And in this case, it's what we call planar, right? It's in a plane. All of these lobes are in one plane, and they're separated by 120 degrees. So this is going to be important for this structure. So all in the same plane, separated by 120 degrees. So when we have a structure of carbon that's based off of sp2, again, each one of these wants to bond because it's half filled. So if it bonds with another carbon, as you can kind of see here, these lobes are going to interact and share their electrons to get to that full configuration. So it's going to share those electrons here, here, and here. And you can see that this honeycomb hexagonal pattern emerges. So this is often called a honeycomb, but it's in plane. And this is what we see with graphite. We see this honeycomb structure. So one carbon bonded to three other carbons in the plane, and those are the sp2 bonds. And then what happens is there's another plane below it and another plane below it, like you see with hexagonal structures, where you basically have a AB configuration, and the bonding between the planes. So something's holding it together, and it's actually those leftover. If I go back, it's that leftover p orbital. This is a fairly weak bond. Oops, sorry. It's a fairly weak bond, but that leftover p orbital is what's holding together the various sheets or planes in this structure. All right, so let's kind of think beyond carbon now. So we talked about sp2 and sp3 first. So what other elements do you think might form into the sp3 hybrid orbitals that you saw with carbon? So think about that for a minute. Pause the video, and we'll actually start with a new one, but see if you can come up with what types of atoms besides carbon will form in the sp3 orbitals. All right, so let's take a look at this question again. So again, besides carbon, what might have this sp3? And to answer that, you want to think about what other elements might have similar electronic or valence structure. And if we go back to our periodic table, we remember that the period or columns have similar valence structures. So if we find carbon here, right, anything in this column we'd expect would have a similar valence structure, only carbon is n equal 2, silicon is n equal 3. So basically it just has a higher number. And so anything in this column or period would have a similar structure. And sure enough, we see that silicon will also form, and also germanium will also form into these structures, as well as these tend to have those types of structures as well. So basically that was kind of what we were looking for, is something in this column that would have a similar valence structure.